afternoon, everybody. Well, first of all, I thank you for the invitation, because this is the second time I come here, so it's I'm honored to join this workshop. And as you see from the presentation, I came here presenting sort of my very recent work on the material point method. And indeed, this is let's say, as you see from the co-author of this presentation, this is the first joint activity that we had in common. A student of Professor Xie joined Deltares in September, and we basically started to looking at the application of this material point method on some of the cases that are very sensitive to Deltares, to the Taiwanese experience. So what I'm going to do is just to present basically the method, material point method, and then also some recent applications that we have been carried out with another university in Italy, University of Salerno, about the use of inverse modeling to optimize the calibration of the method, and then the last application will be the simulation of one of the landslide here in Taiwan. So as you see, basically landslide are characterized by let's say, a movement of let's say, a part of a soil or rock mass that, of course, there are triggering factors that put in a condition, the failing condition, so that this mass moves. But of course, the question are twofold. What are the factors that trigger the motion and or the movement, and how far does it go? So basically, with this method that I've let's say developed with other colleagues, basically we can, in principle, describe not only the triggering part but also the runout distance. So there are many approaches that you can use to simulate a large deformation analysis. One approach could be the Lagrangian approach. You see that the material is attached to the grid, and the grid is moving. But of course, you end up with this situation where the soil fails, and then you have some elements that are too distorted. So there are techniques to mitigate this, but you have some also problems in, for example, remeshing. Another method is, of course, some approaches could be the U-linear approach. You can widely use in fluid mechanics, but there are also other problems. So mesh is fixed and material flows through it, but of course, some important parameter, key parameter, like the state parameters of the soil or history-dependent material cannot it's not, let's say, well captured with these methods. So a combination of both Lagrangian and Eulerian is the material point method, basically. The mass and all information, state variable and stresses are stored in the material points. And this information are mapped to the nodes. Equilibrium, momentum balance equation are solved at the nodes. You move the nodes, or you say you calculate incremental displacement, and you map this incremental displacement to the nodes, and then you move the points. And every time step you do the same. You map information to the nodes, you solve the equilibrium, you go forward. So this solves both problems, so mesh deformation. So in this case, the mesh doesn't move. State variables are stored in the material point, so there is no diffusion. And this is basically an example. Probably this is the soil column collapse. You see the mesh remains the same. Mass of the particles are, let's say, stored in material points. Then material points move and flow through the mesh. Of course, this example shows only a collapse of dry material, but you can also describe as many information as you want. You can couple system with water. For example, you can include saturated materials, so you can describe on these points, you can carry information of water and soil, but also you can include gas, so unsaturated material. And this is a very powerful tool that, of course, can, as I said, you can describe all these levels from, if we focus on one point, you can describe as dry material, saturated material, and also unsaturated material, but you can also include several set of points. For example, one for, in this case, one for soil or solid particles and one for the liquid. In this case, you can simulate both, let's say, dry soil, saturated soil, when these two are in the same mesh or in the same element, and also the free water, when you have only water particles. So this is also a very powerful application. But if we stick to the landslide, there's also a problem of defining soil properties. And most of the time, the use of the right constituent model is the first question. First understanding the problem, then of course you choose the right constituent model and also define the correct soil parameters. And those are not, let's say, trivial. Because you have to, of course, do a lot of investigation, do labs test, but most of the time it's very helpful to, let's say, improve your soil characterization or definition of soil parameters by doing just inverse modeling. What is the inverse analysis? Basically, you have, for example, a slope that failed. You can define, for example, let's say the ground surface position, okay, after a slope failure. Then you basically you run your model. That can be anything. You can be SPH or NPM or FEM model, and then you have a simulation. Of course, the simulation does not match with the observation. So you check how much is the error. And of course, if the error is too much, then you do inverse modeling. So you re-update your parameter with some criteria. You do, again, your simulation. You try to match the data. And with this loop, you end up with, let's say, an optimal set of parameters for a given mesh, for a given problem, for a given constituent model. And that sometimes is very helpful to understand how sensitive is your model on the results, because this is not the only information you can get, but you can also do an automatic test of how sensitive are each parameter on the results. I'm showing a couple of examples before going into the large-scale test. But first, laboratory scale test. This is a lab scale test on a dry material, just to show how this inverse modeling works. So we have a bunch of, let's say, a bunch of sand on an inclined slope, and then what happens is that the barrier is removed, and then the sand is moving towards along the slope, and then reach the equilibrium after a given, let's say, a certain distance. And you see some images here on the right side, where you have some for a given time instant, you have the position of the sand along the slope. Of course, what happens that we made up we define a model. Of course, you see a barrier here, a set of material points, and the mesh. At the base of the bottom of the mesh, you have a contact for a given that has the properties. And of course, this example, and you see on the right side here the simulation. You release the contact, you release the boundary, and then you see the material moving downward. So reaching the equilibrium here at the end. Of course, we use a very simple constituent model, a more Coulomb, and we had certain given properties here at the bottom of the domain. We let's say in order to do inverse analysis, we define for every step here, for every let's say for a given distance here, a certain number of points where we measure the ground surface, like the highest particle for a given location. So we define a contour of the ground surface. And then you see that, for example, there is an observation here, and the model gives different results. So this is an example of how to capture for a given, for every time instance, the ground surface. We define all position of points, and then for a given buffer, we found out the highest particle, and then this is the contour of the ground surface. And this will be compared against those observations. So what we did is we initialized the values to some reasonable initial values. We give some perturbation. We changed a little bit the values, of course, in an automatic way. And we come up with this index, which is gives you the sensitivity of the results to the input parameters. And then you see that the largest, as you expect, the largest sensitivity is given to the friction angle of the soil and the contact of the base. So what we did then is we play only on these two, which are the most sensitive parameter. And then we try to match in an automatic way. You see iterations, and we change the friction angle, the contact friction, and then we found out the optimal set of parameter that gives the best fit. And this is in line, let's say, with the previous study that just did the parametrics analysis on, let's say, in a standard way. But this is, let's say, an automatic tool that can give you the, let's say, a result. And you see that with this given set, you can also include all observation that you can find, also in different time instance, and compare. Of course, in certain cases, you have, let's say, not a good match. In some others, you have a better match. But of course, with this tool, you can add as many let's say, observation as you want. And of course, the algorithm is just calculating and match and give you the best fit for everything. Of course, the things are not that simple, but so what we did is that, okay, we moved to a saturated condition. So this is another lab scale test where we have, let's say, 1 meter slope, let's say here of sand, let's say this is a material, a very loosely packed material with the groundwater table here. What happens is that they have a reservoir here, they increase the hydraulic head here, so what happens is that the groundwater level rises, and then trigger a landslide here from the toe backward. And then you see that you first trigger the toe, and then you move backward for in different stages. So they recorded this. And we use this as, let's say, a validation case. We had, of course, the grain size distribution curve of the soil, the hydraulic conductivity, minimum maximum density, and some triaxial tests, some tests that have been conducted in different studies. We use those. And you see that the material is, let's say, material is very loosely packed, but and then this is the behavior in undrained triaxial tests for those tests. And what we did, we had to use a very complex, more complex material model than just a more Coulomb. We used the hypoplastic model, which can capture the behavior of the soil that can capture also the excess pore water pressure development, especially when we are dealing with liquefaction. So what we did is, of course, this is the list of parameters. It's very time-consuming to do an inverse modeling on all these properties. So we calibrated, we fixed some values, and we calibrated on some of those which are the most sensitive. And you see that we can match the experimental data on the triaxial test in terms of pore pressure development and also deviatoric stress versus axial strain. what we did is that, okay, we start simulating the landslide, and you see that some mechanism, we already also try to use other constituent model, but the key phenomenon here is the liquefaction. So if you have a model that can capture liquefaction, then you can simulate this process correctly. So what happens again is the liquefaction, the failure happens at the toe, and then this is the, let's say, deviatoric strain that are induced in the soil. And if we, of course, it's not plotted here, but if you see the contour of mean effective stress or excess water pressure, you see that the location of liquefaction, or let's say the mean effective stress, are basically zero in this line, which means that you have let's say liquefaction occurring at this stage while failing. Of course, what happens is that you see that some of this let's say fit quite well, but we also use inverse modeling to adjust and to find out what is maybe there's another set of parameter, especially we use one of those, which is the most sensitive, which is alpha, in order to see if there's an alpha that can match better the final results. And so in this case, you see, let's say, the sensitivity of the model, the constituent model on the behavior, and you get more understanding of what is the potentials of the constituent model in the analysis. And you see that basically by changing inverse analysis on alpha, you can get much nicer fit, especially on the run out and the behavior of the let's say the final configuration of the slope compared to the original set of parameters. If we move to a field scale test, this is a very, let's say, a beginning of the study. We just started, let's say, a couple of months ago, just looking at using MPM on a real case on the landslide, and we chose the Shaolin landslide, which is a very let's say catastrophic event in Taiwan. I'm not an expert on this. There are many of you that already know much more than I possibly know on this case. But basically, it was very interesting also on my side to came to know also this the importance of this catastrophic event. And it happens in 2009. Some let's say. This is the cumulative rainfall, and basically we have in 3 days, 3 days or something like 2 meters of rain in total that fall in the region, and that triggered the event. Of course, since 2009, there are many attempts to back calculate the catastrophic event, and especially by looking at the field survey, measurements, laboratory tests, and also some numerical modeling. But let's say what was to my understanding, what was missing was of course, understanding what was the reason of the triggering, and also if it's possible to see the run out in one, let's say, in a single numerical method. And so that going from the triggering point from all the way to the final configuration, and basically here this is the let's say map from top. Then you see let's say this is some cross section. So the cross section AA this is represented here. And then this is a cross-section that is represented here. So you see, this is the ground level before landslide. So you see the blue contour here. And this part of the material moves downwards, part depositing here, but most of the material is moved on this side. So what we decided to do is that, okay, we started very basic, very simple. We tried to use a 2D approach. And let's say modeling this, let's say, cross-section and including this cross-section. So from this part, moving on this side. Of course, this is an approximation. We have to see how much is the different from reality. So what happens is that, to observe from the observation, what I came to know is that part of the shale material, let's say, was failing, and then run off the sandstone, and then deposited at the bottom of the valley. So there have been many, let's say, some tests. I'm not, let's say, some tests, for example, some lab tests on simple shear test on the rock, on the sandstone, and but also some permeability test, and they showed some an interval between 10⁻³ and 10⁻⁶. So the material is very, let's say, there are joints, or the permeability is large. But the measurements of permeability was conducted in several points of the sliding mass. Some next to the triggering, let's say original configuration, and some other in the transition zone, and some other in the depositional area. And so some other tests has also been performed in different locations using different type of material, let's say, and basically they came up with let's say, set of strength parameters. They found out that basically the dry material as of the shale is basically, let's say, around 38 or 40 degrees, with a sort of a bit of cohesion. This is the results of the simple shear test. But if you put this material on the water for some time, then there's been, what I came to know is that the material is susceptible to some expansion, some swelling, and also the strength decreased to 20, let's say, 24, 26 degrees. So what we try to do is to, as I said, to develop a model that, let's say, show the shale. You see this is the boundary, this is the ground level here, before the landslide occurred. And this is the bottom. The contact is basically the contact between the shale and the sandstone. Assuming that there is no effect between the, let's say, sandstone and shale. We give just a given set of parameters along the contact. Of course, the contact has been divided in some zone. The contact properties between the shale and the sandstone is a function of the stress condition, is the, let's say, material property of the shale. And this is, for example, this is the numerical model. This is the mesh. You see, this is the material where the initial soil is, or sandstone is located, and then you see this is a close-up view of this zone, of this part. Of course, as I said, there are some scenarios we made. The assumption is basically that for a heavy rainfall, we have some infiltration depth. And of course, the infiltration depth gets the material saturated. And of course, this is just a strong approximation. And then if the material gets wet, then you change the soil parameters, so the strength decreases. And then, of course, we see the failure and the runout. So what we focus here is that now what happens that if the depth of the infiltration is only 20 meters, we get basically a superficial failure of the slope on top of the dry material. If the failure is getting larger, then you see failure of course, and again on the wet material. But of course, if the infiltration depth gets deeper and deeper, then basically there's no anymore any effect of the infiltration depth, because basically let's say the material that is already part of the sliding mass is moving, and the rest of the material is not moving it anymore. So what's showing here is that this method can show what part of the material is moving, and without predefining the results up front. What we see here is that, of course, if we draw a line of the final configuration after failure, you see that this is the simulation, this is the ground surface after failure. And if we compare all these lines against the observation, you see that basically, let's say the depth of infiltration of 80 meters is basically the most representative one, most close to the observation. Then if we look at the runout, then we say, okay, along this contact we see, we've set the 20 degrees of friction angle, or 15 or 10. You see that the sliding mass is, the larger the friction angle is, then of course the less is the runout. But of course then what you see is that the first part is reaching a certain, let's say, a certain runout, and then the following part is coming and filling the gap behind. Of course, again, if you draw the line, if you draw the ground surface at the end of the simulation, you compare against the results. So you see that basically 10 degrees overestimate the runout. The blue line, the brown line is the ground surface at the end of the observation, and you see that basically the 15 degrees is the one who matches the results. And this value is not different than the value that other people found. Basically, it could be also a little bit lower than 15 degrees, so it might also be in the same range as other people found. And of course, if you see the simulation, then basically the toe of the slope is starting and then backward, then you see some movement of the soil backward, then basically follow the first part that is moving. And so this is also an interesting, let's say, mechanism that may represent what happens in reality, but I am very far from saying that this could be a realistic scenario. Of course, at the end of this study, we said, okay, we could use this model to, let's say, to simulate from the triggering in a very rough way for a couple of scenarios. We don't simulate the infiltration, but we just, let's say, roughly, we change the soil parameter and we see the mechanism. We can improve that. We can improve this kind of scenario by just also, for example, progressively putting some infiltration water and changing the pore pressure and also soil property. But of course, what we can conclude is that this method, or at least for this side of constituent model, can reproduce what happens, at least what we see in field observations. And of course, but the soil model needs to be, let's say, improved in the sense that especially for runout, we need to use other source of dissipation of energy. For example, let's say block collision or other, let's say, way of the rate effect, for example, or energy dissipation to particle collision. And that might be also affecting the runout distance. And at the end, we can use the inverse modeling to see how the importance are the soil parameter in the failure process. We'll see in the future for others. Thanks a lot.